Understanding networking is the key to make your application faster, more reliable, and most importantly, secure. And today I'm going to break it all down for you. First, why should you care about networking in DevOps? Every DevOps engineer interacts with network daily, whether it's setting up load balancer or managing cloud infrastructure. Networking connects your systems, your services, and ultimately your users. Let's break this down, starting with the backbone of any network, the TCP IP model. The TCP IP model is like the blueprint of how data travels across a network. It has 4 layers: the application layer, the transport layer, the internet layer, and the network access layer. Think of each layer as a step in a relay race. Now we are going to try and break down each layer step by step. First is the application layer. The application layer is the topmost layer of the TCP IP model where most users interact with the network even if they don't realize it. Think of it as the gateway between humans and the digital world. When you send an email, upload a photo, or browse a website, this layer is responsible for preparing your data so that it can be transmitted over the network. Let's break down some of the most common application layer protocol and their specific codes. One is HTTP and HTTPS. Hypertext Transfer Protocol and Hypertext Transfer Protocol Secure. This protocol powers the web. HTTP is used for browsing websites, while HTTPS adds encryption to keep your data secure. It is the reason you can view videos, load images, and interact with web apps securely. Next is SMTP, Simple Mail Transfer Protocol. This protocol is like the postal service for emails. It is used to send outgoing messages from your email client to the recipient's mail server. Next is FTP, File Transfer Protocol. FTP is used for transferring files between a client and a server. It is often used by developers to upload or download large files from servers. Let's take a real-world example. What happens when you type google.com into your browser? So the browser recognizes that you are making an HTTP or HTTPS request. It contacts a DNS server to translate google.com into an IP address. The browser will then package your request, asking the server for a web page you want to load. The prepared request is passed to the next layer in the TCP IP stack for transmission. Now let's see what happens when this data moves to the transport layer. The transport layer is where the data delivery happens. It ensures that data gets from point A to point B accurately in the correct sequence. Now let's break this down into 2 key players, TCP and UDP. TCP, which means Transmission Control Protocol, is all about reliability. Imagine sending a letter with number pages to a friend. Each page represents a data packet, and TCP makes sure that all the pages arrive in order before delivering the full letter. Here's how TCP achieves this. TCP creates a connection between the sender and the receiver using a process called the two-way handshake. TCP uses sequence numbers to keep track of the packet. If a packet is lost or arrives out of the order, the receiver requests a retransmission. TCP includes error checking mechanism to ensure data integrity. So if only packet is corrupted, it is retransmitted. Every packet sent is acknowledged by the receiver. This ensures that the sender knows the data has been successfully received. TCP is ideal for applications where accuracy is critical. Think of this. Imagine your email arriving with missing words. TCP ensures it doesn't happen. That's why it is the backbone of this kind of task. Now UDP, User Data RAM Protocol, is a whole different story. Think of it as a speedster. It is fast, lightweight, but not very reliable. Unlike TCP, UDP doesn't establish a connection or check for missing packets. Here's how UDP works. There is no handshake. Data is sent without first verifying if the receiver is ready. Packets are sent individually and may arrive out of order or not at all. Once the data is sent, UDP doesn't wait to confirm if it was received. UDP is perfect for scenarios where speed matters more than accuracy, just like in video streaming or online game. Think of UDP like pizza delivery without receipts. It is quick and efficient, but if a slice goes missing, you might not notice. Now let's compare the two to help you remember their differences. TCP ensures all reliable data delivery, while UDP doesn't guarantee reliable data delivery. TCP is slower due to reliability checks. UDP is faster due to minimal overhead. TCP requires a connection, while UDP doesn't require a connection. Some of the use cases of TCP are browsing, emails, and file transfer. Some of the use cases of UDP is streaming and gaming. So where reliability is key, go with TCP. Or when speed is your priority, go with UDP. Now that you understand the transport layer, let's move on to the next layer, the internet layer. So this is where IP addresses comes into play. This layer is responsible for addressing and routing, two critical processes that makes communication across the internet possible. At the heart of the internet layer is the IP, known as the Internet Protocol. Think of the IP as the postal service of the internet. It adds a source address where the packet is coming from and a destination address where it's going. Without these addresses, your data will be lost in cyberspace. Imagine sending a package. You need to know the recipient's address and include your return address. So IP works the same way for data packets. You're probably heard of IPv4 and IPv6. These are the two versions of IP used today. IPv4 uses a 32-bit address system. It supports about 400 billion unique addresses. IPv4 has been around since the early days of the internet. But with the explosion of devices like smartphones, IoT gadgets, even smart fridge, we are running out of IPv4 addresses. IPv6 is a solution to the address shortage. So IPv6, which is Internet Protocol version 6, uses a 128-bit address system. Now, once our data packets have their source and destination address, the next challenge is figuring out the best path to their destination, which is called routing. Routers are the heroes here. Think of them as traffic managers ensuring package takes the fastest and most efficient routes. So here's how it happens. A packet leaves your device with a destination address. Based on the destination, the router decides which path to send the packet along. Now let's see this in action. When you load the web page, your browser sends a request to the website server. The packet is giving your device IP address as a source and the server IP address as a destination. Routers along the way analyze the destination IP, figure out the best route, and pass the packet along. When the server receives your request, it sends a response back following the same process, but in reverse. Now, to make routing even more efficient, we use something called subnetting. It's a way of dividing a large network into smaller subnetworks or subnets. Subnetting is often defined using side initials. This tells the router how many addresses are in the subnet and helps it forward packets more accurately. We also have network address translation. It's a technology that allows multiple devices in a private network to share a single public IP address. Your router has a public IP address assigned by your ISP. Your devices like your laptop, phones, smart TV use private IP address. So this translates the private IP into the public IP when your packets leave your network, and vice versa when your packet comes back. In DevOps, the internet layer is crucial for understanding how applications communicate across networks. Whether you're configuring a Kubernetes cluster, troubleshooting connectivity issues, or optimizing load balancers, mastering this layer will give you a massive edge. Now the final layer, the network access layer. So this is the foundation of TCP IP model. It is where the actual physical transmission of data takes place. So this layer interacts with hardware like network adapters, routers, switches, Wi-Fi access points, and cellular towers to make sure that your data is transmitted over the physical medium. This layer handles two main responsibilities. One is framing. So before data is sent, it is broken into frames. Each frame includes the actual data and the metadata like the MAC address of the sender and the receiver. Two is physical transmission. Frames are converted into electrical signals, radio waves, or light pulses, depending on the medium. So these signals travel over cables, airwaves, or fiber optic cables to their destination. You have probably heard of MAC addresses before. But why are they important? So every network device like your laptop, phone, or router has a unique MAC address, like a fingerprint. So the MAC address ensures that the frames are delivered to the correct device within a local network. Think of it like sending a letter. The MAC address is a house number that ensures that the letter gets to the right mailbox. Now let's see how this works in a real-world setup. Imagine you're streaming a movie on your laptop. Your laptop Wi-Fi adapter converts the data into radio signals. So this signal travels to your router, which decodes them and forwards the data. On the other end, the router of the streaming service sends data back to your laptop using the same process. So the network access layer is where it all begins, converting your data into signals and sending it out into the world. Whether you're streaming, browsing, or uploading, this layer makes it happen. Now let's connect everything together with a simple example. In the application layer, when you type pogo.com into your browser, HTTP prepares your request. In the transport layer, TCP breaks the request into packets and ensures that they will be reassembled correctly. In the internet layer, IP adds the destination address and routes the packets. In the network access layer, the packets are transmitted over Wi-Fi to your router, then to the internet. Once the server processes your request, it sends the web page back to you through the same layer but in reverse. As a DevOps engineer, you work with TCP IP model daily, from configuring virtual networks in cloud, troubleshooting connectivity issues, or optimizing application performance. Mastering this model will make you a better problem solver. If you found this video helpful, hit the like and subscribe button and let me know what you want to learn next in the comment section.